April 7, 1943, 0847 hours, 23,000 feet above the Solomon Islands. Lieutenant Commander Saburo Sakai of the Imperial Japanese Navy's 251st Fighter Squadron adjusted his oxygen mask as he scanned the brilliant Pacific sky through the canopy of his Mitsubishi A6M0. The morning sun painted the scattered clouds below in shades of gold and amber, while the tropical air remained crystal clear at altitude. Sakai had been flying combat missions for over 2 years, his Zero accumulating 64 confirmed kills across the Pacific theater. What he couldn't know was that the aircraft approaching from the northeast would demonstrate an American technological achievement that would fundamentally alter the mathematics of aerial combat in the Pacific. The sleek, gull-winged fighters diving toward his formation at an impossible 400 miles per hour represented not just superior engineering, but the full industrial might of a nation that had transformed its entire economy into an instrument of war. The F4U Corsairs had just revealed a capability that would shatter Japanese assumptions about American aircraft design and change the tactical dynamics of every air battle that followed. The strategic situation in the Pacific by early 1943 had reached a critical juncture that would determine the outcome of the entire war. Following the devastating Japanese attack on Pearl Harbor and their subsequent rapid expansion across the Pacific, American forces had begun their methodical counteroffensive through the island chains leading toward Japan itself. The Solomon Islands campaign represented the first major test of American industrial production against Japanese military expertise, with both sides committing their most advanced aircraft and most experienced pilots to the struggle for air superiority. Japanese commanders had based their entire Pacific strategy on the assumption that their Zero fighters, with their exceptional maneuverability and experienced pilots, could maintain air superiority despite being outnumbered. The Zero had dominated Pacific skies since 1940. Its lightweight construction and powerful Nakajima Sakae radial engine providing unmatched agility in dogfighting situations. American pilots had learned to avoid turning fights with Zeros, instead relying on hit-and-run tactics that played to their aircraft's superior diving speed and firepower. However, the introduction of the F4U Corsair represented a quantum leap in American fighter capability that Japanese intelligence had failed to fully comprehend. The technical development that led to the Corsair's revolutionary performance began in 1938 when Chance Vought Corporation received a U.S. Navy contract to develop the most powerful fighter aircraft possible around the largest available engine. The Pratt Whitney R-2800 double-wasp radial engine, producing 2,000 horsepower, required a massive propeller to efficiently convert that power into thrust. The engineering challenge was immense: how to provide sufficient ground clearance for a 13-foot, 4-inch propeller while maintaining the structural integrity needed for carrier operations and high-speed flight. Vaught's solution was the distinctive inverted gull-wing design that became the Corsair's signature feature. This configuration allowed the main landing gear to be shorter and lighter while providing the necessary propeller clearance, but it also created unexpected aerodynamic advantages that wouldn't be fully understood until combat testing began. The wing design, combined with the aircraft's robust construction, enabled diving speeds that exceeded anything previously achieved by American fighters. Production of the Corsair began at Chance Vought's Stratford, Connecticut facility in June 1942, with additional manufacturing contracts awarded to Goodyear and Brewster corporations to meet Navy demand. By early 1943, the three manufacturers were producing over 200 Corsairs per month, a production rate that Japanese industry could not hope to match with their most advanced fighters. The mathematical superiority of the Corsair over the Zero became undeniable when examined through the lens of pure performance statistics. The F4U Corsair weighed 9,205 pounds empty compared to the Zero's 3,704 pounds, but this additional weight translated directly into structural strength and diving capability. The Corsair's maximum diving speed of 450 miles per hour exceeded the Zero's structural limits by over 100 miles per hour, while its service ceiling of 36,900 feet provided a significant altitude advantage over the Zero's 32,800 10-foot ceiling. The American fighter's armament consisted of 6 50-caliber Browning machine guns with 400 rounds per gun, delivering a weight of fire nearly triple that of the Zero's 2 20mm cannon and 2 7.7mm machine guns. Perhaps most critically, the Corsair's robust construction allowed it to absorb battle damage that would destroy a Zero, with multiple fuel tanks, armor plating, and redundant systems providing survivability that Japanese designers had sacrificed for weight savings. The Pratt Whitney R-2800 engine produced 2,000 horsepower compared to the Zero's 940 horsepower Nakajima Sakai. But American production capacity meant that replacement engines were readily available, while Japanese pilots often flew with worn power plants that reduced performance significantly. The statistics told the story of American industrial supremacy. While Japan struggled to produce 50 Zeros per month by 1943, American factories were delivering over 300 Corsairs monthly, with production rates continuing to increase throughout the war. The operational reality of the Corsair's combat performance created tactical advantages that fundamentally changed the nature of Pacific air warfare. The aircraft's exceptional diving speed allowed American pilots to engage Japanese formations at will, diving from altitude to attack, and then using their superior speed to disengage before Zero pilots could respond effectively. This boom and zoom tactic exploited the Corsair's strengths while avoiding the turning fights where the Zero's lighter weight and superior maneuverability provided advantages. The Corsair's robust construction meant that pilots could perform high G maneuvers during combat that would structurally damage lighter Japanese aircraft, while the powerful engine provided climb rates that allowed rapid altitude recovery after diving attacks. Training American pilots to exploit these advantages required extensive flight instruction that emphasized energy management and tactical discipline, with pilots learning to use altitude and speed rather than traditional dogfighting techniques. The logistical support systems that sustained Corsair operations demonstrated American organizational superiority as much as technological advancement. Maintenance crews were trained on standardized procedures that allowed rapid engine changes and repairs, while the robust design meant that aircraft could operate from primitive airfields with minimal ground support equipment. Spare parts availability never became the critical limitation that plagued Japanese operations, with American supply lines delivering replacement components faster than combat could consume them. Japanese attempts to counter the Corsair's advantages revealed the limitations of their industrial and technological base in ways that would prove decisive for the war's outcome. Initial encounters with the new American fighter left Zero pilots struggling to understand how an aircraft could dive at such extreme speeds without structural failure, with many assuming that American pilots were suicidal rather than recognizing superior engineering. Technical intelligence gathered from crashed Corsairs revealed construction techniques and materials that Japanese industry could not replicate, particularly the advanced aluminum alloys and manufacturing processes that provided strength without excessive weight. Communication intercepts from Japanese units frequently mentioned the psychological impact of facing American fighters that could attack and escape at will, with pilot morale suffering as traditional tactics proved ineffective. captured documents from the 251st Fighter Squadron revealed desperate attempts to develop new combat techniques, including high-altitude interceptions and coordinated group attacks, but these required fuel consumption and pilot training resources that Japan could no longer afford. Enemy commanders recognized that the Corsair represented not just a superior individual aircraft, but evidence of American industrial capacity that could produce such sophisticated weapons in overwhelming numbers. Post-war interrogations of Japanese pilots consistently emphasized their shock at encountering American aircraft that combined superior performance with apparent unlimited availability, contrasting sharply with their own experience of flying worn aircraft with increasingly scarce replacement parts. The human dimension of this technological superiority emerged through the personal accounts of those who witnessed the Corsair's combat debut in the Solomon Islands. Lieutenant Robert Hansen of VMF 215, who would become one of the war's leading Corsair aces, described his first combat mission in a letter to his family. The Zero pilots tried their usual tactics, pulling into tight turns and attempting to force us into a dogfight. What they didn't expect was our ability to dive away at speeds they couldn't match, then climb back to altitude for another attack. We could choose when and where to fight, while they were forced to react to our initiatives. Technical Sergeant James Morrison, a Marine Corps mechanic responsible for maintaining Corsair engines, noted in his diary, "The Pratt Whitney R-2800 is a marvel of American engineering. We can run these engines at full power for extended periods without the reliability problems that plague captured Japanese engines. The pilots know they can depend on maximum performance when they need it most." Major Gregory Boyington, commanding officer of the famous Black Sheep Squadron, wrote extensively about the Corsair's psychological impact. Japanese pilots, who had dominated Pacific skies for 2 years, suddenly found themselves facing an American fighter that was faster, more heavily armed, and capable of absorbing damage that would down any Zero. The confidence that comes from superior equipment is immeasurable in combat situations. The Japanese perspective on encountering the Corsair revealed the profound psychological impact of facing technologically superior opponents. Lieutenant Hiroshi Nishizawa, one of Japan's leading aces, wrote in his diary after his first encounter with Corsairs, "The American fighters dive at speeds that seem impossible, their engines roaring with power that our Zeros cannot match. We have trained for years in the art of aerial combat, but these new aircraft change all the rules we have learned." Captain Masajiro Kawato of the 204th Fighter Squadron reported to his superiors, "The enemy's new fighter demonstrates industrial capabilities that we cannot hope to match, while we struggle to maintain our existing aircraft with limited spare parts. The Americans deploy new fighters with performance that exceeds our best designs." Technical analysis reports from captured Japanese documents revealed desperate attempts to understand Corsair construction techniques, with engineers noting, "The American aircraft demonstrates manufacturing precision and material quality that our current production methods cannot achieve. The engine alone represents a level of metallurgy and precision manufacturing that would require complete retooling of our industrial base. Intelligence assessments from the Imperial Japanese Navy's Technical Bureau acknowledge the broader implications. The F4U Corsair represents not merely a superior individual aircraft, but evidence of American industrial capacity that can produce such sophisticated weapons in quantities that will overwhelm our defensive capabilities." Post-war interviews with surviving Japanese pilots consistently emphasized their recognition that the Corsair's introduction marked a fundamental shift in the Pacific Air War, with technological superiority replacing pilot skill as the primary determinant of an aerial combat outcomes. American Industrial might reach its full expression in the Corsair production program, which demonstrated manufacturing capabilities that no other nation could match during World War II. The primary production facility at Chance Vaught's Stratford, Connecticut plant employed over 25,000 workers operating around the clock shifts to meet Navy demand, with the factory floor covering 1.2 million square feet of manufacturing space. Quality control systems ensured that each aircraft met rigorous Navy specifications, with test pilots conducting acceptance flights that verified performance standards before delivery to combat units. The Pratt Whitney R-2800 engine production line in East Hartford, Connecticut, produced over 125,000 engines during the war, with each power plant requiring over 1,500 precision machine components manufactured to tolerances measured in thousandths of an inch. Raw material consumption for Corsair production included 15,000 pounds of aluminum alloy per aircraft, sourced from mines and smelters across North America that operated at maximum capacity throughout the war. By comparison, Japanese Zero production peaked at fewer than 11,000 total aircraft during the entire war, while American factories delivered over 12,500 Corsairs between 1942 and 1945. The logistical network that supported Corsair operations included specialized transport ships, mobile repair facilities, and training commands that prepared pilots and maintenance crews faster than combat could eliminate them. The innovation pipeline that created the Corsair's technological advantages demonstrated the depth of American research and development capabilities that Japanese industry could not replicate. University partnerships with institutions like MIT and Caltech provided advanced research in aerodynamics, metallurgy, and propulsion systems that directly contributed to the aircraft's superior performance. Corporate research laboratories at Pratt Whitney, Chance Vaught, and dozens of subcontractors conducted continuous improvement programs that incorporated combat feedback into design modifications. Testing facilities included wind tunnels, engine test cells, and flight test centers that validated performance claims before production commitments, ensuring that delivered aircraft met or exceeded specifications. The continuous improvement process meant that later, Corsair variants incorporated lessons learned from combat operations with enhanced armor, improved armament, and refined aerodynamics that maintained technological superiority throughout the war. Japanese aircraft development, by contrast, remained largely static due to resource limitations and industrial capacity constraints that prevented major design improvements once production began. The resource abundance that sustained American Corsair production stood in stark contrast to Japanese manufacturing limitations that became increasingly severe as the war progressed. American aluminum production exceeded 1.5 million tons annually by 1943, while Japanese aluminum output peaked at fewer than 200,000 tons per year. Energy consumption for aircraft manufacturing drew from electrical generating capacity that exceeded Japan's total national output, with American factories operating at power levels that Japanese industry could not sustain. Transportation networks moved raw materials, components, and finished aircraft across continental distances using rail, road, and waterway systems that dwarfed Japanese logistical capabilities. The apparent waste in American production methods, with prototype aircraft discarded after testing and production lines retooled for improved variants, represented resources that Japanese manufacturers could never afford to expend. This abundance extended to pilot training, with American flight schools graduating thousands of new pilots annually, while Japanese training programs contracted due to fuel shortages and aircraft availability constraints. The immediate tactical changes resulting from Corsair deployment fundamentally altered the mathematics of aerial combat in the Pacific theater. Japanese formations that had previously engaged American fighters on equal terms found themselves unable to force decisive engagements, with Corsair pilots dictating the terms of combat through superior speed and climbing ability. Traditional zero tactics that relied on tight turning fights became obsolete when facing opponents who could disengage at will and return with altitude and speed advantages. Enemy doctrine required complete revision to address American fighters that combined superior performance with overwhelming numerical superiority, but Japanese training resources could not support the extensive retraining required. The cascading effects extended to other military systems, with Japanese bomber formations requiring larger fighter escorts that reduced their operational range and payload capacity. Training programs for new Japanese pilots had to emphasize defensive tactics rather than the aggressive techniques that had proven successful earlier in the war. But shortened training periods due to fuel shortages meant that new pilots lacked the skills necessary for survival against experienced American opponents flying superior aircraft. Strategic realignment within the Japanese military reflected growing recognition that American industrial superiority made ultimate victory impossible through conventional means. Resource allocation shifted toward defensive preparations and special attack units as traditional fighter operations proved increasingly ineffective against American technological advantages. Timeline acceleration of desperate measures, including kamikaze attacks, resulted partly from the recognition that conventional air combat could no longer achieve strategic objectives against opponents with unlimited aircraft replacement capability. Allied coordination improved as American aircraft performance allowed more aggressive operations with reduced risk, enabling strategic bombing campaigns and amphibious assaults that would have been impossible without air superiority. The psychological impact on Japanese military leadership extended beyond tactical considerations to fundamental questions about the nation's ability to continue effective resistance against an opponent with such overwhelming industrial advantages. The psychological warfare dimension of Corsair operations proved as significant as the aircraft's technical capabilities in determining the war's outcome. American pilot morale soared as they gained confidence in equipment that provided decisive advantages over previously superior opponents, with this confidence translating into more aggressive tactics and higher mission success rates. Japanese pilot morale deteriorated as experienced aviators recognized that their training and skill advantages could no longer compensate for inferior equipment, leading to defensive mindsets that reduced combat effectiveness. Propaganda value of American technological superiority extended beyond military circles to civilian populations on both sides, with Japanese civilians beginning to question official claims about the war's progress, while American industrial workers gained motivation from evidence that their efforts were producing decisive advantages. Enemy attempts to counter the psychological effects through propaganda emphasizing pilot spirit and fighting determination became increasingly ineffective as combat results demonstrated the reality of American material superiority. The long-term impact on Japanese military thinking extended well beyond the immediate war, with post-war military planners recognizing that future conflicts would be determined primarily by industrial capacity and technological innovation, rather than traditional military virtues. The verdict of history regarding the F4U Corsairs' impact on Pacific air warfare became clear through both immediate combat results and post-war analysis by military historians and former enemies. The aircraft's introduction marked the beginning of absolute American air superiority in the Pacific, with Japanese forces never again achieving the air combat parity that had characterized earlier phases of the war. specific battles such as the defense of Rabaul and the Philippine Sea engagement demonstrated the Corsairs' decisive impact, with American forces achieving kill ratios exceeding 10-1 against previously competitive opponents. Enemy acknowledgement of the aircraft's significance appeared in captured documents and post-war interviews, with Japanese commanders consistently identifying the Corsair as a turning point that made continued resistance increasingly futile. The technological legacy extended far beyond World War II, with the aircraft's design principles influencing jet fighter development and establishing American aerospace superiority that continued through the Cold War period. Post-war recognition of the Corsair's historical significance came from both Allied and former enemy sources, providing comprehensive validation of its impact on the war's outcome. German and Japanese technical teams that examined captured American aircraft after the war consistently noted the superior manufacturing quality and advanced design features that their own industries could not have replicated. Historical analysis by military academies and defense research institutions identified the Corsair as a prime example of how industrial capacity could be successfully converted into decisive military advantage. The aircraft's influence on future warfare doctrine emphasized the critical importance of technological superiority in determining combat outcomes, lessons that shaped military procurement and development strategies throughout the remainder of the 20th century. April 7, 1943. 8:47 hours, Lieutenant Commander Sakai's Zero, once the undisputed master of Pacific skies, found itself outclassed by an American industrial achievement that represented more than superior engineering. The F4U Corsairs diving at 400 miles per hour without structural failure demonstrated a nation's complete commitment to victory through technological and industrial supremacy. The mathematics of war had fundamentally changed, and Japan's most experienced pilots could only watch as American industry rewrote the rules of aerial combat with aircraft that combined devastating performance with unlimited availability. Like and share this exploration of American industrial might, and subscribe for more stories of how superior technology and manufacturing capacity determined the outcome of World War II.